Hi everyone, myself Suchitra. Today we are going to discuss about the UV spectroscopy. Let us know about the electromagnetic radiations. Radiations are produced by the collision of electric charge and magnetic field residing on the atom. Electric field residing and magnetic components are mutually perpendicular to each other and are coplanar. These are characteristics by their wavelength or frequencies or wave number. The energy carried by an electromagnetic radiation is directly proportional to its frequency. The emission or absorption of radiation is quantized, and each quantum of radiation is called photon. Here the wave is propagating in the magnetic field and electric field. Here the magnetic field is represented by blue color and electric field is represented by the red color. The distance between the two curves is called the wavelength and it is denoted by the lambda, and the lambda is inversely proportional to the energy. Electromagnetic spectrum. The arrangement of all types of electromagnetic radiation in the increasing order of their wavelength or decreasing frequencies is known as the electromagnetic spectrum. Here, as the wavelength increases, the energy decreases, and here the different types of radiations like gamma rays, X-rays, UV rays, infrared rays, and etc. are shown along with their wavelength. Let us move on to the UV visible spectroscopy. UV visible spectroscopy requires the high energy. The ultraviolet region corresponds to the 200 to 400 nanometer and visible region 400 to 800 nanometer. UV region is further divided into near UV and far UV. Far UV is also called as the vacuum UV because the molecules of air absorb the radiation in this region, and this region is accessible only with the special vacuum equipment. And passing the electromagnetic radiation in UV and visible region through a compound with multiple bands, a portion of light is normally absorbed by the compound. The amount of absorption depends on wavelength of radiation structure of compound. Since the absorption of light is due to the subtraction of energy from the radiation beam, when in electron in orbitals of high energies, this electron excitation phenomenon, that is wavelength maximum and strength of absorption and molar absorptivity is defined by the Beer-Lambert's law. Beer-Lambert's law is stated by John Heinrich Lambert, and it stated that concentration and path length are directly proportional to the absorption of light. That is, A is equals to epsilon LC, where A is the amount of light absorbed for a particular wavelength by the sample, epsilon is the molar extinction coefficient, L is the distance covered by the light through the solution, C is the concentration of the absorbing species. Types of electronic transition. Usually the electrons transition is by the four types, that is the sigma to sigma star, pi to pi star, and n to sigma star and n to pi star. Next, here the sigma and pi are the bonding orbitals and the n is the non-bonding orbit, and the pi star and sigma star the anti-bonding orbit. Let us move on to the sigma to sigma star transition. In this transition, the electron in a molecule moves from the bonding sigma orbitals to its anti-bonding sigma star orbitals. This transition takes place due to the electromagnetic radiation that gets absorbed. The highest quantity of energy is needed to undergo this transition. It can be observed in the methane molecules due to the presence of only CH bond. Here in between the C and H only sigma bond is present, and hence these types of alkanes are undergoes the sigma to sigma star transition. Pi to pi star transition. In this transition, electron moves from bonding orbital pi to anti-bonding pi star. Its energy requirement ranges between the energy required for n to pi star and n to sigma star. Organic compounds like aromatic ones, alkenes, alkynes, nitriles, carbonyl compounds display these types of transition. Next, move on to the n to sigma star transition. In this transition, the electrons from a non-bonding orbitals move to the anti-bonding sigma star orbitals. The lowest quantity of energy needed to undergo this transition. The halogen and the elements like sulfur, oxygen, and nitrogen display this transition. Into pi star transition. In this transition, the electron from non-bonding orbital n move to the anti-bonding pi star orbital. The lowest quantity of energy is needed to undergo this transition. Halogens and elements like sulfur, oxygen, and nitrogen display this transition. Here, the lone pair of electron present in the halogens and the sulfurs, oxygen, nitrogens, they are absorbs the electromagnetic radiation, and they goes to pi star and sigma star antibonding orbitals. Here the energy required for transition of n to pi star is lesser than to n to sigma star transition. Thank you.